Namaskar, welcome back. So, last lecture we discussed about the different scenarios of erosion and deposition, and we were looking at that what type of landforms will develop and the evidence will be preserved uh, on the surface in terms of the terraces, in terms of the terrace risers and all that. So, now as I told that we will be moving to the compressional tectonic environment, but before we move to that, let us see one part which we should have done before, but anyway at several instances I have mentioned that part. Now, this is related to your the stress. Okay, so you have like uh, sigma, if we take sigma 1, sigma 2, sigma 3, and that so sigma 1 is of course uh, uh, sigma 2, sigma 1 is greater than your sigma. So, this is max actually. Okay, this is maximum, and then you have sigma 2, and then you have uh, sigma 3. Okay, so this one is your minimum. Okay. Now, how this relation we take in terms of your sigma 1, sigma 2, sigma 3, which is sigma 1 is the maximum one, and in geological settings. Okay, and mainly related to, so one is the your geological setting, and then second part is we are talking in terms of the tectonics. Okay, so in what way this stresses will play an important role, like max to minimum one. So, usually it has been taken into consideration that this all stresses sigma 1, sigma 2, sigma 3, they are uh, mutually perpendicular to each other. This is one point which we should keep in mind. Now, we take different scenarios which we have already, one part which we have already done is the normal faulting scenario. So, if we put that in 3D, then uh, how this stresses will be effective. Okay, so we know this that in under the your normal faulting environment, so you have uh, one of the block will move down, that is your hanging block. Okay, so let us put first the scenarios what we are trying to see. So this is your surface here, and then you have so this surface is here. So this part is basically important to just having an understanding of that. Okay, so let us put here that this is your hanging wall and this is your foot wall. So hanging wall is will be moving down. Okay, so this and this is your what we have discussed earlier also, that this is your fault scarp, and the fault is along this line. Okay, so this is your fault. So, one thing that we should keep in mind that this is here, then the tectonic environment is extensional, and what we see is the normal faulting. Again, this may vary up to as around equal to 90 degrees also. It may be vertical also at some point of time, and mostly it has been seen that it ranges from 50 to 60 degrees or so. That is the fault angle you are talking about. Now, coming to another part is your thrust faulting. Okay, so this part also we have, now we are going to discuss about the reverse faulting environment. So, if we have the block which has moved up. Okay, so with respect to your foot wall. Okay, so if we try to put here in 3D, and slowly we'll come down to the talking about the your uh, so let us just first put this. Okay, so we have a reverse faulting here, where this block has, so here which this block has moved down actually. Okay, so movement is like this, whereas this one is moving up. So this is your fault is here. So if we take this one will be the fault. Okay. And right now we are unable to see the fault plane because it is on the other side, but this is your, what we can say, this will be your fault scarp. Okay. And in this again, as we have been talking about, that in reverse faulting environment, the hanging wall will move up, okay, with respect to the footwall. So this is your hanging wall and this is your footwall. So and then finally what we have is your strike slip faulting. Okay, so for example we have a block which is again in 3D. If we put, okay, so we have a sort of a movement where one block has moved away from with respect to another one. Okay. So this is your fault scarp, and this block has moved away from us and this is towards us. So this I have already explained in the last lecture also. So this is like coming towards us and this is moving away from us. Okay. So this is a typical of a left lateral strike slip movement, and this one will be your fault scarp here. Now there can be a sort of an oblique movement where the combination of we can say, if we say this 1, let us say this 2 and then 3. So you can have combination of 1 and 2, you may have combination of 1 and 3. Okay. So this combination, if we see, then we term this as an oblique slip faults. I'll try to sketch if possible that how we will be able to see that. Okay. So for example, if you're having a sort of an normal faulting along with a slip, okay, then how it will look like. Okay, so you have, suppose this block has also moved down. Okay, so you have the slip, lateral slip, as well as you see a sort of an. So if this type of slip has been seen, okay, then in that case you have this movement also as well as the movement along the fault here. Okay. So this is what you will be able to look at, and that can be reverse also, where if you see this part here, then we can have a right lateral movement also. Okay, so where one block will move towards us with respect to the other one. Okay, so there are different situations depending on the slip. We can justify or we can identify and categorize the type of faulting. Okay, so here what we see is this block is moving towards us and this is away. Okay, so this is moving towards us and this is away from us. Okay, so this will be this is left lateral, and since it is moving along the strike, okay, so this will be the strike of the fault. Okay, so this is, it is moving, of course there is a fault also, but the strike is this one. So hence we term this as an left lateral strike slip falls, and this will become your right lateral. This will be right lateral strike slip fault. So we have the a combination of two, and we have pure deformation. So this will be, if you this you see you come across, then these are what we have. So here we have the combination of 1, and you have 1 and 3. Sorry, this will be 3 you can put here. Okay, this is not 1 and 2, this is 1 and 3, and then 1 and 2 and 3. Sorry, so this will be let me correct this part here. So this will be your 1, that is normal faulting, plus the strike slip, and then you have 2 and strike slip. Okay. So in this case, what we see is we have the combination of 1, and then we have lateral slip, that is 3. Okay. So these are termed as oblique slip faults. Okay. So just make this correction. Okay. This is bit more 1 because this is your normal, and then strike slip, reverse, and then strike slip. Now coming back to the stresses what we are talking about. So we see that you have like sigma 1, sigma 2, and maybe you can say the sigma 3. Okay. So how it will be effective in terms of different faulting. Now, as I told that if we consider this relationship of sigma 1, sigma 2, sigma 3, where we have the in geological setting, we take this as and they are mutually perpendicular to one another. And then in different tectonic environment, how it will be actually. Let us see for the normal faulting environment, or we can say this as an extensional tectonic environment. So in this case, what we will have is we will have the least will be perpendicular to the plane. Okay, that is your sigma 3, and then along the plane you will have sigma 2, and vertically, because the block is moving down. Okay, so then we say this is sigma 1. Okay, so maximum will be vertical. Okay, so if we just put this over here, then what we have is that we have sigma 1. Okay, you have sigma 1 over here, then you have along the plane you have sigma 2, and then perpendicular to the plane where it is moving, you can say this is sigma 3. Now in case of reverse, what we will see is that you have the least along the plane. Okay, so that is your sigma 2, and again over here, because this block is been this is a compression here. Okay, because it is seeing, and in the first one we were seeing that the block is moving down, so sigma 1 is the maximum over there, but here we will have this as an sigma 1. Okay, and then sigma 3 will be your almost vertical. So this will be the difference for that. Okay, so sigma 3 is here you have, then sigma 1, and then along the fault you have your sigma 2. Okay. And further, in the case of your strike slip faulting, what you have is, since the block is moving horizontally, then you have sigma 1 over here. Okay. And then sigma 3 will be perpendicular to that, and then sigma 2 will be vertical. Okay. So this part you should keep in mind when we are talking about the different tectonic environments. So this will be the second one will be your compressional tectonics. Okay, And in this, as we have already discussed, but let me just put it here, we will see reverse faulting and we will see thrust. And this is based on angle. Okay, if the angle of the fault is less than 45 degrees, we classify this as thrust. If it is greater than 45 degrees, then we classify this as in reverse fault. And in this, we have what we call is a strike slip environment. Okay, and in this one, we have right lateral strike slip, and then we have left lateral strike slip. And then we have also discussed that we can have the combination of this 1 and 3 and 2 and 3, which we will term this as an oblique slip fault. So, I hope this is clear to you, and then we will move ahead with the compressional tectonic environment, and we will see what are the landforms and how we can study the trenches across this one. Another thing which before we move ahead, in last lecture we discussed about that after the formation of scarp. Okay, so I am just putting this in 2D. So, if you have a normal faulting, okay, if you have a normal faulting like this, okay, so initially this is the movement is along this fault, okay, where you have this block has moved down, okay, and after the erosion of the scarp, how it we will see is something like this, okay, or maybe you can say further like this, where you have the colluvial wedges and all that. Okay, so you have the scarp finally left out, something like this. And in case of the reverse also, if suppose this block has moved up, okay, suppose you have the block which has moved up here like this, okay. So after the erosion, what you will see is this is so. The point what I'm trying to tell you is that topography remains more or less similar actually, okay, of in the case of the normal fault and the reverse fault. Okay, so that we will have to keep in mind, because the fault here in this case is like this here, and in this case it is something here. Okay, this is. Now let us move ahead with the compressional tectonic environment. Okay, so compressional tectonic environment, how we see the signatures of reverse fault and the thrust fault. Okay, so most widespread tectonic environment are the area of converging plate, and that is mostly we can see in areas like what you are having the subduction zones. Okay, and of course we have the collision zone also. So these are all subduction zones, and this part we have already discussed in the plate tectonics part. Okay, so these are all we will see. This comes under the compressional tectonic environment. Okay. So subduction zones, okay, transform faults, if they are oblique, then we will see the compression over there also. Okay. So these are the most prominent areas where you will expect compressional tectonic environment. So the Earth's major earthquakes have occurred along the circum-Pacific ring of fire, okay, belt of plate convergence, and continental collision. Okay. So best example is your Mediterranean and the Himalayan zone. Okay. So you have zone of continental collision, that is between Indian plate and Eurasian plate, or Asian plate you say, or Tibetan plate. That is the very one of the most prominent examples from the or areas in terms of the collision. Okay, so subduction zone and collision zone in northern Africa, Southern Europe and Middle East, and along local compression tectonic environments, that is along stepovers in strike slip environment in some back arc regions. Okay. Now, style of deformation, if we take the large magnitude earthquakes in compressional tectonic environment produces surface rupture represented by displacements on reverse or thrust faults. Okay. That part we have discussed that in the previous slides, that we will come across reverse and thrust faults in compressional tectonic environment. Okay. Now, surface manifestation is either in form of scarp. Okay. So, scarp basically we will say that okay fine, it will be something like this. Okay. So, these are your fault scarps. This is after the erosion has occurred. Okay. So, this is will be your fault scarp here, and then this line will be your fault line. Okay. So, either in the form of the scarp or fold or by change in the elevation of the surface. So, what basically it has been suggesting, suppose you are having this flat surface now and there is a deformation which goes and the push is there from this side. Okay. So, you will have the formation of the scarp, fold scarp also, that also we term, and then that there will be a change in the elevation. This two were at the same elevation, but now it has moved up. Okay. So, change in the land level surface, but not all changes we see in the topographic variation is related to faulting. One has to be very careful. So, most common structure in compressional tectonic environment is your thrust faulting. Okay. And usually thrust faults bifurcates. Okay. When they are projected towards the surface, and that what we call the imbricated fault systems. Okay. So, in section if we see uh, this type of faulting or related deformation, and what we are terming as like imbricated thrust system, that basically indicates like there is a faulting which has moved the deformation along the faulting here. Okay. So, it may move further, okay, propagate further. Uh, if we say this is north and this is south, so then we are looking at the south propagation of this faults. Okay. So, these are termed as imbricated fault or thrust system. Okay. Now, further what we see is that at depth, the depth of this bifurcated faults decreases. So, for example, if we have the fault here, then it goes down and then it decreases. Okay. So, you have deformation which is going on along this, okay, and then you have the decrease in the, and that what we call the, that is until they merge. For example, you have one fault here and then another fault is coming like this. Okay. So, this merging of the fault at the depth, okay, we term this as an décollement or detachment. Okay. So, the bifurcated faults are this one here, and further the décollement at low angle, that is in low angle structure, typically thrust separating more deformed rocks above the plane from the less deformed rocks below. Okay. And that is what we term this as an your décollement. Okay. So, décollement is, so one is your bifurcation of the faults here, and this low lying plane will term this is been termed as décollement. So, décollement is a low angle structure, typically a thrust, separating more deformed rocks above from less deformed rocks below. Okay. So, you have more deformed rocks here than less deformed rocks here. Okay. Now this has been related to here, like, or with the ongoing deformation in Himalayas also, and that what we say, because the process remains almost similar here, that you have a detachment here, okay, and that is what we are talking about, the basal décollement, and this push has resulted into the formation of different faults, okay, and that is your imbricated faults, okay. So this process overall is been termed or categorized as the bulldozing effect, okay. So we'll stop here and we'll continue in the next lecture talking more on the thrust faults and reverse faulting environment. Thank you so much. Namaskar.